project is plotting the orbit of an asteroid, and my name is Emerick. And my research center was actually my own high school, Freeport High School, and my mentor was my science director, Dr. Vincent Pereira. Do all of you have the title down?
Go. This is going to be not that comprehensive because of the fact that, well, I want to, talk more than read. So let's start out with asteroids. Asteroids are bodies that are made up of debris left over from the formation of the solar system close to 4.6 billion years ago, 5 billion years ago, actually. And they are found in 3 places in bulk around the sun. Do any of you know where exactly asteroids are found? The 3 places. The asteroid belt, in between Mars and Jupiter, the Kuiper belt, just beyond the orbit of Pluto, and the Oort cloud, which is over 3 billion miles away from the sun. It still orbits around the sun. Their orbits are governed by Newton's law of gravity, and that dictates that an asteroid will orbit in an ellipse, which I will elaborate upon further in the presentation. The orbits are, wow. There we go. The orbits are governed by this equation, F equals G, mass of object 1 times mass of object 2 over R raised to the 2nd power. I will tell you what this means. F, well, F, it can mean force or it can mean a variety of other things. In this case, it's the, well, it is force actually, the force of gravity that's exerted upon the orbit of the object. G.
Sorry, you guys are making too much noise, okay? Please show respect for Emerick. Sorry,
F is force of gravity exerted upon an object that's orbiting around another object. G is the gravitational constant, and as the name implies, a constant is just a constant variable. It never changes in value. M1 will be the mass of the sun, and M2 would be the mass of the asteroid. R equals distance, and that is raised to the 2nd power. The goal of this project is to use physics to plot the orbit of asteroids in relation to the Earth and the Sun. And my ultimate goal is actually to make like a 3D movie out of it, and to show everyone like where the asteroid will be, at what time and what place, and in relation to the Earth and the Sun, and where the Earth will be, and where the asteroid will be as well. Now this is what my project is based off of, the ellipse. The ellipse, everything in the universe orbits around another object. If a body in space is to orbit around another object, it would do it in an ellipse, which is essentially an eccentric circle. And in other words, it's an oval. And there are several key aspects of the ellipse I would like to touch upon. Mainly the focal points representing, where's the laser? This one? Yeah. The focal points represented by F. If this were this is the focal point of this particular ellipse. The closest focal point to object P would represent the sun. Object P would represent the asteroid. And an ellipse is governed by the semi-major and semi-minor axes. The semi-major axes are the larger of the axes, and semi-minor axes are the smaller ones. Kepler's equation can be used to solve for an ellipse, but you can use other equations to solve for ellipses as well, because there are so many different mathematical terms you can apply to an ellipse, and this Eccentricity. Do any of you know what eccentricity is? Well, I forgot to, I was going to ask for that. Well, eccentricity is any number ranging from 0 to 1 that determines the extreme tendencies of the ellipse. Now, if you were to say raise the eccentricity of a circle of an ellipse to 1, if I'm not mistaken, you'd end up getting a perfect circle. And if you were to lower it, you'd end up getting a blank line. I'm like just a line. Because if you lower it to 0.001, that's what you get, a line. And that's actually just an extreme ellipse. As I mentioned before, there are many equations you can use to solve one ellipse. This is one of them. R plus R1 equals 2A. R equals A 1 minus E squared over 1E cosine theta. And theta, since it's not really a number. And, well, I use MATLAB in order to simplify these equations and to eliminate the human error problem. Because if you have, there's a lot of values that you have to work with when working with ellipses, and this just simplifies it all. If I'm not mistaken, Continental uses it too. Wow. Okay. The methodology, materials. Well, since it's math intensive, I didn't really have to use that many things. I mean, all I had to do was use a computer and MATLAB whenever I wanted to write a program in terms of solving a mathematical equation. So, I mean, you already have the equations and you don't really need much else besides the computer. And you need the footage of various asteroids because you can't work with theoretical asteroids if you really want to plot their orbits, methods. Well, given the gravitational constant and the mass of the sun, you can write a program that calculates the distance and the mass of the objects. Once the distance from the sun is given, you can calculate the changes in the angle theta for a given period of time using Kepler's equation. Then plot the ellipse using MATLAB. Am I going too fast?
No.
There are no conclusive results as of yet because my mentor is actually a very busy person. In fact, I haven't been to him over a week. But yeah, there aren't very many conclusions except like objects that are farther away tend to have more eccentric orbits. And the references, well, there was only really one reference that I really used. It was an introduction to astronomy book, just to look up random facts and the acknowledgments. Dr. Vincent Pereira, my mentor. Freeport High School, Dr. Sat Bhattacharya, the HCS staff, the audience. Are there any questions? Huh? Okay. Can you read that? Any other questions in the meantime? Yeah.
Yeah, I have a question. My question is like, you measure asteroids, right? Like, well, how do you know the velocity of an asteroid? How fast it goes?
The velocity, I think that is measured by another equation. I haven't really been introduced to that particular equation yet, but there is a particular equation. It's I really don't remember the equation itself because I'm still learning tons of math.
Right. So I believe when an asteroid like travels,
but you can take the velocity from the circumference of the sun, how far it is, and the time it takes for the asteroid to actually orbit the sun.
that's actually measured in years, so you're working with a decimal number.
So basically, you should estimate the velocity and so we don't know exactly what's going
But yeah, pretty much.
You can do that.
Anybody else? Kenneth?
So, I'm not sure if this is more of a question or more of a problem with what you were doing with your experiment, or suggestion. But I know that for every year, since you're doing this in relation to the sun and the earth, I know that the earth doesn't follow the same exact pathway around the sun each and every year that passes. It actually moves around the sun in the same elliptical orbit, but it changes its position every year. So, would you, so when you're, with your asteroid data, are you going to just compare it to one single year in comparison to the sun and the earth, or are you?
Yeah, one pathway that the earth takes during a given year.
All right.
Yes?
When you guys measure the asteroids, do you guys just count their position?
We actually do use tons. We do use tons. Yes.
Can you further explain the
Ellipse. Ellipses, you want me to go back to the slide?
Yeah.
Alright, an ellipse is actually the pathway that any given object follows when it's orbiting another object. So the asteroid itself would actually follow a pathway, and I know that this particular picture sucks. I know. The asteroid will follow a given pathway because given the distance from the two focal points, represented by F1 and F2, and given the mass of the object itself, because the more massive an object is, obviously the more gravity it exerts. And if you remember correctly, Kepler came up with this, if I'm not mistaken. He decided that everything isn't constant in the universe, and that things are irregular, and hence the ellipse. Because if I remember from before, the model that Newton proposed said that everything orbited in a perfect circle, but Kepler noticed irregularities in this and concluded that there was an ellipse involved, that there was an oval, that everything is the same. And you can have several different types of ellipses. You can have extreme ellipses, like certain planets in foreign systems will orbit very close to their parent star, and then go out, and then come back in really close. And these are called extreme gas giants, if I'm not mistaken, because they tend to be gaseous.